Namaste and a very warm welcome to everyone. We are delighted to have you join us for another exciting session of the Vismay Vigyan YouTube webinar series, a science outreach initiative under the Jigyasa program by CSIR 4th Paradigm Institute, Bengaluru. Today's webinar is titled Weather Forecasting, Myths, Science and the Future, and will be delivered by a leading expert in the field, Dr. Vivekananda Hazra. It is an honor to welcome Dr. Vivekananda Hazra, an atmospheric scientist whose work brings together high-performance computing, advanced numerical weather modeling, and artificial intelligence for tackling real-world weather and climate challenges. Dr. Hazra currently serves as a scientist at CSIR 4PI, Bengaluru, and an assistant professor at the Academy of Scientific and Innovative Research, ACSIR. His research spans CFD, the WRF model, inverse modeling, crop growth simulation, and coupled WRF model. He has previously worked at the National Center for Medium Range Weather Forecasting as a project scientist too, where he contributed to the BIMSTIC Ensemble prediction system and developed the open source WRF IMDAA pre-processing toolbox. Dr. Hazra's award-winning doctoral work at IIT Bhubaneswar used machine learning to identify and correct biases in rainfall modeling. His interdisciplinary expertise is grounded in a PhD in climatic science and technology and a BTech in mechanical engineering, and he is proficient in tools such as OpenFOAM, WRF, Fortran, Python, and HPC environments like Pratyush, Mihir, and Cham. His research has been published in prestigious journals and has been recognized both nationally and internationally. Today, Dr. Hazra will guide us to the fascinating evolution of weather forecasting. The first part of his talk will focus on the common misconceptions about weather forecasting, a brief history of how weather prediction began, how we collect and assimilate data from satellites, radars, balloons, and surface stations, how numerical models use this data to generate forecast. So viewers, what are the biggest myths people believe about weather prediction? How did forecasting evolve from folklore to supercomputers? What kind of data powers today's weather models? Why is data assimilation such a crucial part of forecasting? Let's listen to what Dr. Hazra will present before us. Please join me in welcoming Dr. Vivekananda Hazra as he helps us separate myth from science and give us a glimpse into the exciting future of weather forecasting. Over to you, sir.
Thanks, Reena. And thanks Jigyasa team for having me here. So title of my talk is Weather Forecasting, Myth, Science and the Future. So I hope the target audience would be the students, mostly undergraduate, whoever is in class 10th and up to class 12. So yeah, so I have the contents of my talk would be that common misconceptions or the myths and second the science and the future. So first I'll be discussing about some misconceptions. So we have some kind of sentence that meteorologists just guess the weather, and people actually often joke that meteorology it's kind of a throwing a dart to a board for meteorologist, it's like throwing a dart to a weatherboard. But in practically, meteorologists actually analyze various amounts of data. They simulate using mathematical equations, and they try to simulate these equations in HPC, where much uncertainties actually gets involved while doing this process. But it's not that they just guess the weather. And forecast actually based on models, satellite data, radar data, ground observations, and so many other factors. So this is a myth. Yeah, the second myth is, if it is wrong today, then it's always wrong. And they people try to forget that maybe there is a wrong forecast today, but they would ignore the hundreds of times it was right. And it's can you believe that forecast nowadays are like if you see 1 to 3 days forecast, like 30 years, 20 years back, it will be as accurate as 7+ days forecast of today. And forecast actually based on probabilistic and small changes in the initial conditions, and which generally gives us different outcomes. But you can see the how weather forecasting has evolved over the time. If you see the past 50 years of like statistics, you can see that forecasting has enormously improved over the time. Yeah. And many people actually trust their mobile phones rather than following the weather bulletins, which generally provides by forecasting agencies like IMD, and who are the like authorized organizations for give a like forecast. And they just generally see some app in the phone, and they try to believe, okay, this is going to be like this. And when it doesn't give them the desired result, then they start blaming the meteorologist. But actually the thing is, weather apps actually run on automated system, where like there is a like certain automated system where they would run the model, or they just collect the data and give some sort of forecast, which may not be accurate all the time. So it's recommended that you should follow weather bulletins, which are generally delivered by some authorized organization like India Meteorological Department and some other, rather than following just the apps, the mobile apps. Yeah, this would be the most famous myth that people have, that the opposite prediction myth. So it's always cold when meteorologists say it will be warm, and vice versa. So people love to joke that meteorologists are always wrong, and they should just follow the opposite what they have said. But you will see down my presentation that forecasts are based on probabilities and the errors. There are numerous errors actually that gets generated during this process, which leads to this kind of not, I will say, opposite prediction, but sometimes it gives bad prediction. But this is due to the chaotic nature of the atmosphere. You probably knowing that nature is much chaotic. It's not at all predictable. So this is not actually correct. And the past like 50 years or 60 years, you will see how forecasting has been improved by using of HPCs, high performance computing, and other stuffs. So this is a clear myth, which I would request everyone not to propagate. And yeah, so the another thing is that animals can predict weather better than meteorologists. This is the animal forecaster myth. So people generally say that my dog knew before the rain would be coming, before weather office did. But in practically, meteorologists, they use advanced tools and models. And in some cases, yeah, some animals, they can sense the change in the pressure or the change in the humidity, which leads to them to get some kind of informations, but they cannot be trustable all the time. Better, like, rather you should trust the authorized meteorologists and some weather bulletins rather than following some animals. So this is another like myth that people have in their mind. And some people say, yeah, meteorologists are always wrong about cyclones. This is also not correct. And they often make funny statements that they never go where they are supposed to, as directed or as per the meteorologist. But forecasting has been improved significantly. If you see the statistics of people deaths due to some cyclones, you can see in 50 onwards, in 1970s, there are lakhs of people died due to cyclone. Then if you see some our super cyclone Odisha, the death rate reduced drastically, so it will be in the order of like thousands. And now, like post 2000 or 20s, 21st century current state, if you see, there are like hardly any deaths due to cyclone, because they actually the weather models are much sophisticated nowadays, where they can give you a cone of uncertainty. We call it probabilistic prediction, and mostly it falls between this cone of certainty only. So nowadays, deaths due to cyclone or heavy extreme events has been drastically reduced. So it would be wrong to say that meteorologists are always wrong about cyclones. It has been increased. The prediction capacity has been increased. And yeah, this is maybe another famous myth that weather prediction is very easy. So people often say that how hard it can be. It's just weather. So they don't know that how complex this process could be while predicting the weather, because it's the most challenging fields in the science, and it's a interdisciplinary science where you have to know many other things. So it's not at all easy. It's much complex. And they generally use massive data sets. They have to handle massive data sets, computation, and some very hard, understanding of the atmospheric physics you have to know in depth, rather than like while saying these kind of sentences. This is not at all easy task. You'll be knowing after like few slides that how hard this can be. And this is already discussed that weather prediction hasn't improved over the time, but this is kind of a wrong statement. People may say nowadays also that they still can't get it right, but you can see the 5-day forecast today is as accurate as 2-day forecast, which was like around 25 to 30 years back. So it has been improved. Forecasting has been improved drastically due to some uses of satellites, supercomputers, and our better models. So I have one second. Yeah, so I have mostly covered some of the myths that actually people have in their mind. Now we'll be focusing on the science, like how weather forecasting works. So let us discover, or let us explore this fascinating topic, like how scientists generally predict this unpredictable weather, which affects our day-to-day life, like from where to like how do you go, like where do you go, and how to plan our activities. So weather actually affects everyone in so many ways. So first I would tell you that what is the difference between weather and climate. So weather is like a state of the atmosphere at this current time, and what is going to be like within few time scale, not a larger time scales. So it will be so I'll be discussing some topics like after like the slides. So it's like a current state of atmosphere, and not current state of atmosphere, just a state of atmosphere of a particular region. So like it is to say that people watch the news to see what the weather will be the day, or maybe after 6 hours, or maybe tomorrow, or after like 5 days. But in climate it will be average weather conditions for a region, weather, and it will be for a longer period, for a particular time. So it's may so it can, you can say that the climate of Bangalore is like mild weather with rain. So it is average weather conditions for a particular region climate. So weather prediction, I would say it's much complex than predicting the climate, because it's a long period average kind of statistics. So meteorology. So this is a branch of science which deals with Earth's atmosphere and the physical processes occurring on it. And it generally includes the like humidity, like specific humidity, relative humidity, temperature, cloud coverage, pressure, and other variables like wind speed and other things. So generally they are restricted to the dynamics and thermodynamics of the atmosphere, as it affects the human life. So this is the part of the science where deals with atmospheric thermodynamics and dynamics. So like now, as we already know, the atmosphere. So what is this atmosphere? This is a layer of gases surrounding the planet Earth, which is retained by Earth's gravity. And Earth's atmosphere actually varies horizontally. So if you see the temperature plots and other things which you would be knowing, I guess, that it generally varies. So due to some layers within the atmosphere, and the lower part where actually we generally live, which is called troposphere. So our mostly things will be focused on this troposphere, because we will be bothering about this region only. However, would be the a model, like not only models. So the entire processes would be depend and would affect the entire atmosphere, not only the troposphere, though we live in this particular region. And this parameters which generally get varies due to this throughout these regions are like pressure, temperature, density, and humidity. So now, like, why weather forecasting, why do you need it? As you already know that these are like few broad areas of applications where weather forecasting affects directly, that is mostly the transport, agriculture, hydrometeorology, nuclear, and commerce. Agriculture, as you know, this India's economy is like agricultural driven economy. So we would be focusing more on agriculture, because the summer monsoon and other thing like our winter monsoon. So monsoon rainfall is very crucial for Indian agriculture. uh, so weather forecasting has a largest impact on Indian agriculture, though it will be having not equal, but as well, like as equal as agriculture on transport as well as commerce and other stuffs. So now, like, what do you want to know? So our focused parameters will be to knowing temperature, wind speed and direction, clouds and precipitation, which is the most important parameter that all the meteorologists generally gives much importance on this precipitation term, and visibility and humidity. And not only knowing the parameter, we need to know the trends in all of this, and the changes, and the time of the changes, and lastly the occurrence of extreme events like cyclone, drought, heavy rainfall event, cloud burst, and other stuffs. So now, like how far ahead? So ideally, like we will get to know as far ahead as possible, but in practically, we follow certain terms while like during forecasting, which is called nowcasting. Like just for like after hours, what is going to happen to this particular region, we call it nowcasting. Then it's called short range, reasonable quantitative forecast. This is up to 48 hours. Now extended range forecast, there's for 3 to 5 days. Extended forecast, not extended range forecast, extended forecast, it is for 3 to 5 days. Then we call medium range forecast, which generally up to like 10 days. Then extended range forecasting, which generally varies from 4 to 6 weeks. And we have seasonal forecast also. So like what is going to happen after 2 months kind of stuff also we can also predict. So like brief history, I'll be discussing some of the brief history. It's not visible. I can turn it. So you can see this this is started officially, not officially, like in 1901 when Cleveland Abbey founded weather bureau in US. Then he only suggested that the atmosphere would follow some principles of thermodynamics and dynamics, hydrodynamics. And next is like in 1904 when Buckness proposed that a two-step procedure for model-based weather forecasting. First, an analysis of data, like which is called data assimilation to generate the initial conditions. Then a forecasting steps involving like solving some initial value problems. In 1922, Lewis Rickardson, he carried out the first attempt to perform the weather forecast numerically, like manually. So he followed some manual calculations, but he ended up in getting some like very bad results when he compared his results with like validation kind of thing. That time he actually made some mistakes taking some fast waves in his computation. That time he didn't realize what went wrong. Then in 1950, a team of American meteorologists like Charney, Thompson, and Gates and others, and most importantly von Neumann, they succeeded the first numerical weather prediction using an ENIAC digital computer. But this time they have taken around like 24 hours to predict a 24 hours forecast. So they took around 1 day to even forecast 1 day's like weather. So it was bad, but it was bad compared to today's time. But that time it was the fastest achieved forecast that they could generate, and mostly with much better results. In 1954, Carl Gustav Rosby actually is a Swedish meteorologist, and he actually first operationalized the forecast using a barotropic equations. In 1955, the operational NWP started in US in 1955, and it was a joint like teamwork by NWP unit of US as well as with the US Air Force and Weather Bureau. In 1959, Hinkelmann, he produced the first reasonable primitive equation based forecast, like 37 years after Rickardson's failed attempt. So this time Hinkelmann, he removed some high frequency waves like acoustic waves from equations, governing equations in numerical model. So it was like first time ever that he could achieve a very good reasonable forecast. In 1966, Germany and US, they started producing official operational forecast based on primitive equation. And later in 1972 in UK, in 1977 in Australia, and India was in around like 1980s, like 80 to 84. India started producing official forecast using NWP. So the process of weather prediction actually involves various steps. One, the important component is data collection. Second is data assimilation. Third, modeling, and last, forecasting, disseminating the forecast to the general public. So data collection is like gathering the data from various sources, be it ground-based observations or marine-based or satellite-based. Second point is data assimilation. I'd be telling some idea, like some like concept of data assimilation. Why do you do it? Down the line, and modeling, and then forecasting. So let's look into data collection part. So these are like various sources of data that we generally collect, like from surface observations, some upper air observations, marine, aircraft, satellite. You can see from this schematic diagram that these are like sources of data, how actually we collect the data. And the left portion, you can also see that there are numerous satellites. They generally revolve around the earth, starting from geostationary to polar orbital. So we collect data from various sources, and this time of data collection, there are many errors, like calibration error or human error. They generally gets involved while collecting the data. So these are like some idea about how do we collect data from AWS. We also have AWS stations, automated weather stations, radar, and other stuffs. And in marine, in like ocean, we call buoys and Argo. These are the some types of data that we some types of instruments that we collect the data from, because it's generally get floated in ocean rather than on earth. It will be like stationary, but in ocean it will be kind of moving. So there also we face some challenges. So the most largest data that we get is from like satellite and radars. So like data assimilation technique. Data assimilation, we have like there are like two types of assimilation systems. One is sequential data assimilation, and another is variational data assimilation. Whoever is working on data assimilations, they would be knowing that we call it 3D VAR, like 3D variational assimilation, 3-dimensional variational assimilation, like 4-dimensional variational assimilation, which comes under variational data assimilation technique. And in sequential, we follow Kalman filter or ensemble-Kalman filter. But nowadays, we can also, so it has also been improved by using hybrid 3D VAR or hybrid 4D VAR. Or in sequential, we also see we can see there's hybrid ensemble transform Kalman filter. So it's also gets evolved. So nowadays, the more hybrid terms are getting added to existing thing, and where we take account some other errors also. So I'll give you a brief idea how we collect the data and what is the purpose of this assimilation system. So let us assume this is an Indian domain, like a region. So let us focus on some area. not entirely the Indian region, just to give an idea. So this part, now what you see, what we do, we just create a mesh over this particular region. And now let us assume that we have some sources of data, scattered data over some other regions. One has been connected from AWS, maybe another from satellite, and some other portions from like radar or something. So you can see we have to provide data to data deficit regions. So we'll try to transform this data rich region to data deficient regions. So the process, in this process, we'll try to fill the points by using data assimilation system, not only horizontally but also vertically. So this is the main purpose of data assimilation, where the data would not be, all the data would not be having like accurate. So we'll have to first filter it, process it, or like if it's an instrument, we have to calibrate it. Then we'll get the good amount of data sets. Then using this data sets only, we'll fill the data deficit regions from this data rich region. The process of this this entire system, this is called data assimilation system. And it also so we'll try to get a best atmospheric state of a particular time using data, available data. So this is how actually data assimilation cycle actually it happens. So from analysis, from if you see the left part, so from there we just try to give a very short forecast, which is called first guess. And this green line, it is kind of unknown true atmosphere, unknown true condition of atmosphere, where we like this is what we try to achieve. Then this first guess and observation, for a particular time there will be observations. So this observation and the first guess, and from these two we try to make the analysis. We call it analysis, which is the current state of the atmosphere for the particular time. Then from analysis we try to give a forecast. So if we had given forecast from first guess itself, so you'll see the error would be much higher. So by analysis we will try to make the system as close to observations, but during this time the current state, we would be knowing the current state by the first guess. So this process, this cycle, this analysis cycle, generally in all the operational agencies, they have two cycle, like 00 UTC as well as 12 UTC. These two time they actually do this analysis thing using data assimilation system. So our main, and if you see, this is the time we call it as assimilation window, this time where this assimilation occurs. So our main objective to achieve this green line by using this data assimilation system. So I will stop here for this part 1. So on the next part we will be discussing about modeling, like numerical weather prediction thing, and the future of weather forecasting. Thank you.
Thank you, Dr. Vivekananda Hazra, for that fascinating overview of the world of weather forecasting. We have a few questions. I request Dr. Hazra to please answer them. So, what are some reasons why forecasts might go wrong, and how accurate are they really today?
Yeah. So as I've already discussed, this process actually have so many issues. Like we encounter so many errors while this process, starting from data collection to modeling. So in data collection there would be human errors, so and calibration errors and so many other stuffs. Then during this data assimilation stage we also encounter some kind of errors. Then in modeling, transform these equations to like difference equations, not this PDE. So from partial differential equations, we convert it to partial difference equations. This time also there are some errors where we try to neglect the higher order terms. Then there is error of models. So model error. So during this and even after modeling, we do post processing. So starting from data collection to post processing, there are so many errors those are involved.
Okay.
That's why we get some sort of like errors during the process. But nowadays it has been reduced drastically. If you compare like what was happening like 30 years back, now it has been improved much like higher by. So these are the errors. Because of this source of errors only we get some kind of bad forecasts. So this.
Okay, sir. Thank you. And so when we go ahead with the weather forecast, like a common man tries to look at the weather forecast in the weather app, or it might be in Google. So they just search as weather Bangalore, or they search it like that, and they get a weather prediction for the whole day. But sometimes it happens so that the weather prediction will be accurate for one location, but it is not accurate for the other location. So it shows in percentage, like there is a 30% chance that it might rain at 11 o'clock or 12 o'clock in the afternoon. So how can this be like given as a accurate weather prediction or something? Like how accurate will these be? How can we rely on those data? Like,
That's why these are called probabilistic forecast. You say
Okay.
30%, 70%.
Yes, yes.
We would not say there will be rain. So this is called probabilistic forecast,
Okay.
where you give you some kind of probabilistic numbers. So maybe 90% there will be rain, or maybe 30%. We wouldn't say that in Bangalore will be having rain, but we add one part called probability. So but if you see some weather bulletins, but nowadays also apps are like Google's and other stuffs. They are also using some models where some like AI models are there, where I'd be talking about them in my next part. But they also use some kind of AI enabled models. But I would request people to generally follow to weather bulletins, which is generally disseminated by IMD or other authorized organizations, rather than just following the app. But nowadays it has been improved. It's not like that it will give you some drastic difference results, that it will not be rain, or maybe you'll say like 30% rain, then it had like havoc rainfall. It generally don't happen.
There is no much difference.
Not much difference. It has been introduced, but you can rely. But to give a best estimate, you have to follow bulletins.
Yeah. Okay, sir. So how do the satellites and the ground-based systems work together to provide real-time weather data?
Yeah. So this is just a covered. So we generally collect data from these sources, from ground-based as well as from satellites. Then we try to assimilate it. And not assimilating, so we'll filter out some bad data sets and we'll get the good data sets. Then using these good data sets, we'll try to create a current state of the atmosphere. We call it data assimilation system. By this data assimilation system, we call it analysis. So to create analysis, we'll create a current state, not only horizontally but also vertically. So we'll have a complete idea about what is the current state of the atmosphere. From then only we'll try to predict, because I will cover this numerical weather prediction is an initial value problem. This is not a boundary value problem. So initial value problem means the better you have a good data, the better your forecast will be. So by this assimilation system only, we augment these data sets which are collected from various sources. So this is the process.
Okay. Yes, sir. So what are the biggest challenges that India is facing in collecting accurate weather data across such a diverse geography?
Yeah, so this is a tough job but we have satellites. We have geostationary satellites, many stationary, we have polar orbital. So by satellite data we try to fill all the gaps. But let's suppose we want to put some IoT sensors or some AWS stations. So maintain those stations, it is very challenging, like a task for the agencies. There you have to maintain it regularly. You have to calibrate. You have to visit properly. So this, and if you see this, India is a diverse country. So we need much data stations is like higher orographic area like Himalaya region, all those stuff. So where this model generally gets failed due to we call it like CFL criteria, where we cannot this time step is very important in model. So there we need actually data, and where we are lagging. So maintaining this data stations is very crucial. For that, people are maybe reluctant to because creating one data station is different. So you have to just one time investment, but then maintain it regularly. It is a tough job. But we have because in GTS, in others, all the countries have made an agreement that they would share their data to a common platform, where like NCMWF or IMD most is the like main center for data collection. What they do, they collect all the data throughout the globe in a particular time, and all the country does so. So this is to give you a like a base, because I cannot put a data over US data, like source over US. So we have to rely on their data only. So this is a common platform that we have created. So we call it global telecommunication system, GTS. Through GTS we get all the data, but it's very tough to fill all the data, because you have to, if you intend to get a good forecast, you have to have some good stations, or like many stations throughout the India. But it is not at all possible to give or to put a station or some other stuff to every block, because it leads to money. So much money would be needed for putting this. So but nowadays, for this data assimilation, by data assimilation we can fill those areas. So that's how we call from a data rich region to data sparse regions. So that's how, this is the only otherwise you have to get some funding, or money is actually the problem.
Yeah, thank you, sir.
Yeah.
So in the first part of the webinar, we have unpacked some of the most common misconceptions about weather prediction and seen how they differ from scientific reality. We also took a brief look at the history of weather forecasting, tracing its evolution from traditional observations to today's advanced systems. Importantly, we learned about the vast network of data collection tools, and we gained a clear understanding of data assimilation, the crucial steps that blends this observational data into models to generate reliable forecast. We look forward to the next part of this session, where Dr. Hazra will build on this knowledge and take us into the science challenges and future possibilities of weather and climate forecasting. Thank you, everyone.